Hello and welcome to Buildings of Tomorrow. My name is John Lester and today's episode is another buzzword buster. So if you haven't heard one of these episodes from us in the past, they're a slightly longer format, and basically we pick one of the topics that we discuss within our normal episodes, and we just have a look at a lot of the terms and a lot of the phrases that you hear in the industry and run through with an expert to give a brief description and a definition of those terms. There are so many things changing in our industry. We hear so many terms that perhaps we don't have a full understanding of what they mean. So that is why the buzzword buster exists. And today we are talking about hydronics. I'm joined by Chris Kopp, who is an expert in HVAC theory and hydronics. Chris, thank you very much for joining us.
Hi, John. Thank you very much for having me in this episode.
It is always a pleasure, recorded from home. We keep charging no matter what happens outside, right? Perfect. So today is a buzzword buster. As I mentioned, hydronics is the topic. We're going to dive straight in. We've taken a slightly different approach here. We want to keep it a little organized because a lot of these terms really do refer to each other or related to each other. So we're going to start and run through a bunch of different hydronic buzzwords. And where we're going to start is at something that we've mentioned a few times. We haven't quite got into detail. And the next thing that I have on the list after our discussions is plant characteristics.
Yes. So this basically is an additional topic with relation to these proportional laws, because the plant characteristic is a curve that is based on the second proportional law. And it just shows basically the relationship between the resistance and the volumetric flow in a hydronic network. And because it goes by the square, it is a parabolic curve. And when we draw a graph with, let's say, the volume flow on the x-axis and the resistance on the y-axis, then you can show how your network behaves by drawing this parabolic curve. And that's what we call the plant characteristic.
And how does that, or how can that be applied to a smaller part of the system, the partial plant characteristic?
Yes. So when we say plant characteristic, we normally mean how does the total system behave? So when we look at the total circuit from the producer with the supply lines all the way out to the consumer and then back, we could say with the maximum volume flow and the maximum resistance, we can derive basically how does the complete system behave. But very often we have to break it down and look only at parts of the piping or only look at certain components. And this second proportional law applies on one hand to the complete system setup, but it also applies to an individual component. So for example, if you have a heating coil in an air handling unit and it has a certain resistance at the design flow, then its resistance also goes back by the square when we lower the flow. So by that we can break down a system to all its separate parts, to its components, to different pipe sections, and then basically draw or envision such a parabolic behavior based on the second proportional law for these individual parts and add them up and stack them up in whichever way it makes sense to consider certain behaviors. And this is very often important when we look at part load conditions, because then we have to consider how do certain parts of our system react to a reduced flow, and maybe other parts react in a different way. And then you can really think about, and now what is the situation when I only have 60% of flow? What does that mean for my main distribution lines? What does it mean for a certain consumer? And that then helps very often to figure out how can we handle that with our controls.
Great, thank you.
You're welcome.
Now let's get into, we've talked a lot about variable volumetric flow. To deliver this variable volumetric flow at a system level, we rely on the pumps, and we have variable speed pumps. Can you give us a quick definition or confirmation of what we mean when we say variable speed pumps?
Yes, as you just said, by trying to have variable flow throughout, let's say, the whole network, then of course we need to enlist the help of pumps that can adjust to changing conditions. And when I said before that we now have some preferred hydronic circuits and we want to run variable flow, of course this only became possible once variable speed pumps or variable speed drives for bigger pumps became available and became also available at reasonable cost to be put into place. But today I would say it is standard even in areas where you want to run constant volume flow. Today you probably have a variable speed pump that you then just set to a constant speed because it's much easier to buy such a pump than another one. So we need variable speed pumps, and I think the only thing that we have to keep in mind, unfortunately, we cannot control them between 0 and 100% of volume flow. We can only drive them down maybe to about 30 or 25% of the maximum flow. And below that, we cannot go further down because of the way the EC motors and the variable speed drives are designed and work. And we just have to keep in mind, once we turn on such a pump, it will always run at least, let's say, at 25% of the maximum flow. And this is also something that needs to be then considered when we select the pumps. Sometimes it might even make sense to have two separate pumps at different sizes to really take advantage of varying the flow almost between 0 and 100%.
Okay, perfect. And there are different ways for us to control these variable speed pumps. So let's look now at the next two that we'd like to talk about, or next three: delta P constant, delta P proportional, and delta P constant at the end point of the plant.
Yes. So with variable speed pumps there are also different approaches how we can control them. Because of course we want to vary the speed in order to adjust to the flow, but also in order to adjust to the changing resistance in our network, because as we discussed before with the proportional laws or the affinity laws. So let's focus on the first two, the delta P constant and the delta P proportional, because these are two strategies or approaches that are also implemented by the pump manufacturers. These are two approaches that can easily be selected on a controlled pump, electronically controlled pump, directly by hitting a button or by selecting this strategy, let's say in an app that you have on your mobile phone or so. And delta P constant means just that it maintains the pressure or the pump head, as we say it, that the pump brings at design. It maintains always this amount of pressure. It doesn't go above, but it also doesn't go below. It says, for example, we have 7 meters of water column that we need as pump head at design, and the pump always maintains that amount of pressure, whether it's needed or not. And in order to maintain that at lower volume flows, it will reduce the speed somewhat, a little bit. Unfortunately, this only has, let's say, a small impact on the power consumption, maybe depending on the pump between 10 to, let's say, 25%. Because when we look at the whole situation and at this parabolic curve of the plant characteristic, when you envision such a parabolic curve, we know that it goes down rather dramatically at low flows, which means then maintaining always the constant pump head is a waste, because then our control valve has to take care of the difference, which basically throttles it off as much as it can. And that, of course, is not very efficient from the energy perspective. So that's why we and also the pump manufacturers say, rather than maintaining a constant pump head, why don't we lower the provided pump head continuously, most of the time to a point where at very low flow, we reach about half of what we had as a pump head at design. And that is then often called delta P proportional. And because we lower the pressure that is provided by the pump continuously as we lower the flow, this of course is more energy efficient. And with that approach, if you look at average, let's say, volume flows of about 50%, we can reduce the power consumption already quite interestingly between, let's say, 25 to maybe even up to 40-45% compared to what the pump pulls or draws at design. And these, as I said, are standard approaches that you can normally also select on an electronically controlled pump as a strategy. Now, the next two that I would like to talk about are most often then implemented or are in need of a building automation system. And the first one is that we say, let's have delta P constant somewhere at the end point of the plan, meaning across the consumer and the control valve. So that means we try to figure out how much pressure do we need out there at any given time, and this is what we control to. And experience shows this is usually much lower than what we would achieve with delta P proportional. So it gives us an additional saving possibility, but of course we somehow have to measure the resistance out there and the pressure that we provide at the consumer, which means we have to have ways to connect that to the building automation system and then drive it from there. And that's something a pump itself cannot do because it has no means to measure somewhere out in the hydronic circuit what the actual pressure provided out there is. So that's why I said we need to rely on a building automation system. And that gives us an additional advantage to the standard approaches. If we want to do it the best way we can, we should do it demand-based. And that's a term that is often heard and used, but demand-based means we try to find a way to figure out what the consumers currently need. And I say exactly consumers, not just one, several, because we then can derive from example the valve positions, what is their need. And if we see, for example, that all these valves are throttling down to maybe 40%, this is a clear indicator that the pump at the producer puts way too much pressure into our network because all the valves have to hold against that pressure. So by knowing that, we then can go back through the building automation system and continuously lower the pump speed, for example, by resetting the pressure differential set point for this pump. And the beauty of it is that it reacts to the changes in the dynamic network, because we talked before and said our networks have a dynamic behavior. And sometimes that leads to oversupply, and sometimes that leads to undersupply. With demand-based approach, this is no longer true. We always have exactly what we need out there at any given consumer, because we always check which consumer has the biggest demand, and this one then drives the pump speed and with that the pressure that the pump provides. And this is the most energy efficient way of doing it. But of course, it needs a communicating building automation system, because somehow we have to get the information from the different consumers throughout the building.
Okay, so we covered quite a bit there. We
yes.
looked at two different, let's say, variable speed pump control strategies that are based within the pump themselves. Delta P constant, where you're just maintaining a set point around the pump head. Delta P proportional, where you continually try and step that pump head set point back while still maintaining the required flow, which certainly gives you more advantages than the delta P constant. But that next level, again, by involving a building automation system to actually bring some transparency from the field. And the first one you mentioned was a delta P constant at the endpoint. So picking the part of the of the system which is the furthest away, as an example, from the pump, and making sure that the delta P provided at that point is up to the minimum or the expected requirements, which gives us some transparency at the end point. And we just assume by saying if the people furthest away are getting enough water, then we assume everyone else is getting enough water as well.
Yes,
and then the last
that's
one,
the idea. Yeah.
And then the last one you mentioned was the best, which is not just to look at one single point in the system, but to look at every point in the system where you can not just verify that perhaps the flow is correct, but if you see some consistent behavior from those control systems to say, my whole system is at 50%. That means I'm providing way too much water, so I can dial back even more my set point, because if the valve is open to 100% in every place, and I'm providing the right amount of water, that's my ideal situation. Nothing is wasted. There is no pressure that has to be washed by the valves, and no wasted energy at the pump.
Yes, exactly. And I think with today's, let's say, building automation system setups, where we normally have, let's say, in an office building or so, where we have individual room control for heating, cooling, ventilation, and these controllers are communicating across standard networks like KNX or BACnet or so, then this demand-based pump control is just basically a rather small engineering effort that has to be put into the system, but you gain quite a bit with regards to pump efficiency. And I think this is always worthwhile to do.
Beautiful. Now, the last word on the list that I'd like to cover is something that we just mentioned then when we were describing different strategies to control a variable speed pump, is the pump head, because we mentioned the pump head, but we didn't really talk about what we mean by that phrase.
Yes, so it's a common term that is used in the industry, and it basically means the pressure a pump provides to the network. And pump head is just a term that is used for that. And very often when we talk about pump head, we also use the units meter of water column, which is also kind of a traditional unit. You know, when you look at the SI units, you would rather talk in kilopascals or millibars or bar. But a lot of people have a feeling for what does 1 meter or 7 meters of water column mean with relation to a system setup, because they are used to that and have established a certain, let's say, internal feeling for that, and they can then envision what it means in their situation. And so the pump head is often talked in meters per water column, and when you envision it, it just means the pump would be able to pump the water from a level 0 all the way up to 7 meters. What we have to keep in mind, these meter of water columns are just a picture, because today we have closed circuit systems that are pressurized. So the elevation that we have in a building or so is not what influences this pressure that the pump has to provide the pump head. It's really driven by the resistance in our network created by pipes, by components like heating coils, cooling coils, and so on. But it's a common term, and even in catalogs of pump manufacturers, they show the pressure of pumps in meter of water columns and label it pump head. That's why we brought it up this way.
Okay, perfect. Chris, thank you so much. We've covered a huge amount of different terms, whether they're part of choosing, selecting, and ensuring that we understand correctly the valves that we're putting within the system, the circuits that help make up that system, or the system itself, how we describe it, and how we look at the way that we control the flow and the different approaches that we have in controlling the pumps that deliver that flow and that pressure. Thank you so much, as always, for joining us. We very much enjoy it when you visit me. I get the feeling that we probably have another one of these buzzword busters in us when we want to talk about other components of of the HVAC systems.
Yeah, I think there is more to discuss besides hydronics. I think there are such terms in the heating part, in the cooling part, and also in the ventilation and air conditioning part. For example, VAV and things like that are maybe worthwhile to discuss at another time.
I believe so. I think that if not to scare anyone, but if we have a VAV, an AHU, and an FCU discussion at some point, that will give us a good start for another good buzzword buster for sure.
Yes.
So thank you.
Anytime.
Thank you again, Chris. And thank you to all of you out there for listening to this episode. Please feel free to share, like, and comment on this episode. Subscribe to us on whichever channel you're listening to us right now. Remember to share. And as always, we very much appreciate your time in joining us, and we look forward to seeing you again soon. Thank you.